So we left off talking about the elementary reactions and how they must add up to make the reaction mechanism in total. So they must all add up to the overall balanced equation, and they must agree with the rate law. So if the rate law says that one of the reactants that isn't in your slow step is in the rate law, then your mechanism isn't working. It's not accommodating the exact same thing we're seeing statistically based off of the rate law. So we can't prove a mechanism absolutely, but we can come up with a possible mechanism. This is just how we talk about all science. You don't really prove anything in science. You support it over and over and over again until someone can disprove it. You can disprove science. You can't prove science. So let's apply this. If we write our rate law from an elementary reaction, all you do is you look at your reactants. Okay, my reactants are NO and N2O, and the order comes from their coefficient. So write it now. So for this case, we'd get rate equals K of NO and N2O. If I had had a coefficient of 2 here, then I would have put an order of 2 here. For the next one, the reaction of 2NO2 plus F2 makes 2NO2F is thought to proceed via this two-step mechanism. So instead of all 3 of these colliding at the exact same time, which is statistically very unlikely, what is more likely is one of these NO2s collides with an F2. They have enough energy and they collide in the correct orientation, and that separates the bond of the F2 and creates an NO2F and leaves a free floating F. Now fluoride ions, if we put the little charge for the ion, a fluoride ion is the most reactive element or ion on the periodic table. So if it's the most reactive ion, this very next step is going to happen very quickly. As soon as this fluoride ion is released from this F2, its next collision with the next NO2 that comes by will create a second NO2F. So to see that these add up, if we cancel the intermediate, okay, it was produced and used up very, very quickly. We add these up to our overall reaction, and we get 2 NO2s. Notice we have an NO2 here and an NO2 here, so we have 2 NO2s plus an F2 makes 2 NO2Fs. Okay? I'm just summing these 2 equations together. This is how we know this is a good mechanism, if our steps add up to the overall equation. 2NO2 plus F2 makes 2NO2F. Our steps add up, our elementary steps add up to that overall equation. Now to write the rate law, we look at the slow step. So the rate is K of NO2, F2. Based off of the coefficients, I have a 1 order and a 1 order, a second order overall. When an intermediate is a reactant in the rate determining step, the derivation of the rate law is going to be a little bit more difficult. Okay? What I want you to add here is what we're going to have to use is substitution. Okay, just like in a math class. So if we write our rate law from the slow step, okay, we always write our rate law from the slow step. That gives us R, or rate, equals K times NO3 and CO. The problem here is that NO3 is an intermediate. It's not a starting reactant. Our rate law needs to be something we can use in an actual lab. I can't use this rate law at an actual lab yet. Saying to start with something that's only produced for a short time in this intermediate step doesn't work. Instead, so if I write my rate law from this, I need to replace this NO3, use substitution. Replace this NO3 with something that's equal to the NO3. So if we look at this equation here, we have NO3, and if we manipulate this rate law, we can have something that's equal to NO3. So we're trying to do substitution. Our goal right now is to find something that is equal to this and replace it. So because NO3 was an intermediate, we must come up with something equal to NO3 to substitute it. Well, if you look at the previous step, K of NO2 squared, if you write the rate of this side, equals K NO3 NO. Notice I have a double-sided arrow. Both sides of these could be the reactant, depending on which direction you're looking. Okay? So if I write the rate law on this side and the rate law on this side, the rate of the forward and the reverse are going to be equal. So K NO2 squared, right? There's two NO2s. K NO3 NO. I'm wanting NO3 by itself. Okay, well the K's cancel, right? K is the same. Now we're just doing basic math here. I want NO3 by itself, so I would divide both sides by NO. Do you see that? NO3 is equal to NO2 squared over NO. So now, remember substitution, I will take this and substitute it into my rate law. Okay? So let's walk through that one more time. We write our rate law from our slow step. We have to write it from the slow step. That's what determines the overall rate. But I can't use this in real life. Okay, having NO3 by itself, NO3 is a very active ion. I can't just go get a certain molarity of NO3. It is immediately produced and immediately reacts with something new. So instead of having this as my rate law, I replace it using another step of the same mechanism. So if I look at the previous step, even though this is a fast step, I can find something that would be equal in concentration to this NO3. So NO2 squared equals NO3 to NO. And then I just manipulate it to get NO3 by itself. NO3 equals NO2 squared over NO. Then I can plug this in for NO3. So let's practice one that requires this substitution. So we have the reaction Cl2 reacts with CHCl3 to form HCl and CCl4. This is the hypothetical mechanism with the 3 elementary steps. We write the rate law from the slow step. So we write the rate law from the slow step. Cl, though, is only an intermediate. Okay? It's produced and used up. So I have to replace this Cl with a different Cl. I need to look for one that's in equilibrium so I can compare rates going forwards and backwards. So I'm going to be using this one up here to substitute. Okay. Now this says that I have 2 Cl's per 1 Cl2. And if I write their rate laws, K of Cl2, notice it has a 1 coefficient, so it has a 1 order, is equal to K of Cl squared. So when you have an equilibrium equation, one with a double-sided arrow, you can make their rate laws equal to each other. Because remember, both sides could be the reactants. It just depends on which way you're looking at it. Are you looking at it going in this direction, then these are the reactants, or are you looking at it going in this direction, and these are the reactants? Their K is going to be equal, right? Equilibrium, equal rate. So we have K of Cl2 equals K of Cl to the second order. I need just Cl by itself. Remember, I'm trying to replace this right here. I'm trying to find something to substitute it. So if this side is being squared, the opposite of squaring something, so the square root of Cl2. okay, square root of the concentration of Cl2 is going to be equal to the concentration of Cl. Now we're able to replace this. This was the goal all along, was to find something to replace this intermediate in my rate law. I plug that in. R equals concentration of Cl2 square rooted times CHCl3. Okay. If I was to do a lab, I can do this. If I calculate and I find out I need the square root of 2 molar Cl2, I can do that. I can plug that into a calculator. What is the square root of 2 molar? And then I can go measure that and use that in a lab. This is now a very viable rate law that is based off my slow step. So a model for chemical kinetics. We discussed this in our little intro unit. Molecules must collide to react. That's the only way it's going to occur. They must collide.
Correct orientation.
And only a small portion of collisions are going to produce a reaction. Okay, they have to collide. Because they collide, then we have a chance of a reaction to occur. But when they collide, they must collide with right amount of energy and correct orientation. Okay. Now, increasing the temperature is going to increase their speed. If we increase the speed of those molecules, we're also increasing the likelihood that they collide and the amount of energy they have when they do collide. This is why rate and rate constants often double for every 10-degree increase in temperature. They often double for every 10-degree increase in temperature. Activation energy is the energy that they must have when they collide. The higher the temperature, the more energy they have, so the more likely they are to overcome that activation energy. So when they collide, if they're moving faster, they're going to collide more often, and they'll also obtain more energy, which means they're more likely to get over that activation energy hump, which means you're going to have more of these effective collisions. So the rate of the reaction is going to depend on activation energy, not on delta E, not in the total change in energy, or the delta H, right? Not the delta H. This has no effect on the rate of the reaction. That's just how much energy is absorbed or released overall. No matter how fast that reaction goes, this reaction has a set change in energy. Activation energy is going to directly affect this speed of the reaction. The higher the activation energy, the slower the reaction at a given temperature. Well, the higher the activation energy, then that makes each collision statistically less likely to create a reaction. Okay. Molecules in collisions have varying energies. As temperature increases, more collisions will have sufficient energy to overcome the activation energy. So as temperature doubles, the fraction of effective collisions increases exponentially. So if we're going from 0 to 10 degrees, my reaction rate will about double. If we're going from 1,000 to 1,010 degrees, my reaction rate will about double. Okay, so that 10 degrees, it's an exponential. Every 10 degrees, we're having a doubling effect. Now, even considering activation energy, our reaction rate is still smaller than would be predicted just from number of collisions with energy. That is because of our second factor, molecular orientation. So my two factors are they must have enough sufficient energy to overcome my activation energy, my EA, and they must have the proper molecular orientation. So if we look at the image of these molecules, so we have NOBr. Two NOBr molecules collide to produce a Br2 and two NOs. Some of these orientations create this effect, some do not. If we have these two collide in this vertical orientation, then this collision creates energy right at this bond. This is the bond that needs to break. This is the bond that needs to form. At this orientation, this can happen. So this would be proper orientation. As long as they have enough energy to break and form these bonds, then this would occur. If they collide like this, if these bromines have a direct collision with each other, with enough energy to overcome their activation energy, then we're able to create this reaction again. However, if the oxygens are the ones that collide, this energy is not in the proper orientation. Even if this has plenty of energy to overcome the activation energy is needed to break these bonds over here. That energy is not going to be transferred through the molecule to this bond at the other end. So at this point, they will bounce off one another and continue in their opposite directions, because their collisions are elastic if we were talking about gas molecules. Now the Arrhenius equation. This is the equation that can be used to calculate activation energy. However, this is one of the things that changed when they changed the curriculum of this course. You will not be calculating activation energy. You are going to use this equation conceptually, just like how we use Coulomb's law. So we're going to conceptually use this equation. So the first relationship we need to look at is that activation and K are inversely proportional, which makes sense. The higher the activation energy, the lower the K. The higher the activation energy, the slower the rate. The lower the K, the slower the rate. Okay? Lower K is slower. And K is very temperature dependent, and we can see that based off of this reaction here, or this equation here. Now, a catalyst is one of the main ways we talk about lowering and changing our activation energy. A catalyst is something that speeds up a reaction without being consumed. Okay, it produces a new reaction pathway with a lower activation energy. Catalyst lowers the activation energy for both the forward and the reverse reaction. Because it's lowering the hump on its energy diagram. We've looked at these energy diagrams many, many times. Okay, this is something you really must understand. We use this for several different units of chemistry. These energy diagrams help us understand both the kinetics of a reaction and the energy of a reaction. So with my enzyme, I lower this activation energy. I do not change my delta H. Remember, my delta H is what is the difference between my reactants and my products. This will not change with the change in activation energy. Final concept is a couple of examples of catalysts. A biological catalyst would be an enzyme. Many times biological catalysts, they work to help with that orientation problem. If you think of an organic molecule, those are the ones that are like C22, H44. So these huge molecules, and at the very end they have a little OH or something like that. And when you're hoping that these collide with the correct orientation, meaning out of that giant molecule we want the collision to just occur at this very tail end, that's going to be statistically unlikely. So if we're trying to speed up this reaction, we need something to kind of help with this orientation problem. And that's what a lot of biological enzymes do. They actually hold on. They attract one of these large molecules and hold that OH end in a very certain orientation. And then they attract the next thing that's supposed to bind with it and hold it in a certain orientation, and voila, these two now react together. So this reaction will occur without the enzyme, but it's just statistically very low that they happen to collide with the correct orientation. This enzyme forces them into this correct orientation, so it occurs more and more often. So your body really needs these enzymes. It's like in your mouth, you have amylase to help break down those starch molecules, those huge, giant starch molecules. Okay. Another very important catalyst in your life, especially when that 2:30 bell rings and you guys are all scampering out into the parking lot together and everyone's turning on their car at the same time. All those cars have this nice thing called a catalytic converter. Because what your engine does is it produces carbon monoxide and nitrogen monoxide, both of which are deadly to you. What a catalytic converter does is it uses a catalyzed reaction to change CO and NO2 to CO2 and N2. So you were able to walk by and be just fine. Back whenever we didn't have these catalytic converters, especially in the movies, whenever people talk about how they turn on their car and just sit in their garage, they'd let this build up. Okay. Now we try and produce this. Now, CO2 isn't exactly great for our environment, but it's still better for us. So for now, this is our step. Hopefully, we can find another kind of catalytic converter or just a different kind of engine to help with this problem. But for now, this is a very crucial step to what we're doing.